Hello everyone. In this lecture, our subject is to make a brief introduction to use of numerical methods on engineering problems with this so-called parachutist problem, which is mentioned in your official textbook on several occasions. We will do this analysis in 5 parts, basically. In part 1, we will solve the problem just like in the high schools, with constant gravitational acceleration, and we will not include aerodynamic drag or any aerodynamic effect on the body. In the second part, we will solve the problem again analytically, but this time aerodynamic effects or aerodynamic drag forces will be included. We will do this solution with a little outsourced help, basically from Wolfram Alpha. Again, we will use constant gravitational acceleration and air density values for this part. So in part 3, we will make our own solver using Euler forward formula or Euler forward method in MATLAB, in which again we will use constant gravitational acceleration, constant air density, and aerodynamic drag will be included in this part as well. So in part 4, we will basically modify our solver written in part 3 using the gravitational acceleration and the air density values as a function of altitude. So aerodynamic drag will be included as well. At the final part, we will use MSc Adams software to calculate the motion. Of course, we will do this with both aerodynamic forces are included and are not included, and basically we will use this tool to verify our own solvers, both analytical solvers and numerical solvers, at the final stage. So let me describe the motion first. As you see in this diagram, we have a parachutist, and this parachutist has an initial speed of v0. This v0 may be 0, which makes this problem a free fall problem. It may be a positive or a negative value as well. So also this parachutist has an initial location of z0 with respect to ground level, and he or she has a mass, of course, and he or she has an aerodynamic property. In this problem, we will only have a aerodynamic force in vertical direction. So this corresponds to a aerodynamic drag coefficient, which is denoted by CD here. So before diving into differential equations, we shall define the degree of freedom concept first. So what is degree of freedom? So we can define the degree of freedom as like this: the minimum number of coordinates to define a motion. This motion may be a single body's motion. This may be a mechanism, or this may be a machine, by the way. So in rigid body dynamics, an arbitrary body in space will have 3 translational and 3 rotational degree of freedoms. So if you want to visualize that with this, like this, axis here, we will have x-axis here, and we will have y-axis here. So we will have three translational motions with respect to these axes, and we will also have three rotational motions with respect to those axes for an arbitrary body, let's say. So in total, this system or this body will have 6 degrees of freedoms. So if the motion if the motion is not in a 3D space but on a plane like this xz plane, in this case it is called a planar motion, the body will have two translational motions in x and y axis, and one rotational motion. Let's call this as theta. So in total, this body will have 3 degrees of freedoms. So if we accept this body as a point, so the rotational degree of freedom will be gone, and we will have only two translational degrees of freedom, which means we can define the motion of this point with respect to this fixed frame with two coordinates, x and z coordinates, right? If you look at our particular problem again here, we do not consider the side wind effects, or we do not consider any type of side force in, let's say, x direction. Which means we can solve this problem like a 1 degree of freedom system, whose degree of freedom is only the z axis or z motion on the z axis. So if I can solve the z of t for this problem, then all the motion, that means all the motion is solved. So let's go back to our problem, starting the free body diagram of the motion. So I will basically have a ground like this. This is my ground. On the ground I will have an earth fixed or global axis system. Whose axes are capital Z and capital X. My parachutist is modeled as a point mass. Place it here. I will have another frame on this body with small z and small x. This frame may be called as inertial frame, and this is called the earth fixed frame in multi-body dynamics jargon, by the way. So this point mass has a mass of m, and at initial conditions where t equals to 0, v0 will be equal to basically v0, and z0 will also be equal to z0. If I have to show that, z0 is basically defined with respect to the ground. It is the difference between the initial condition of the inertial frame with respect to the earth fixed frame. I call this as z0. So for the first part, I have already said that I will use this problem just like in high school. So we don't have any aerodynamic force, we only have here the gravitational force because of the gravitational acceleration g, like this, and its magnitude is m times g. Okay, so I'm writing down the equation of motion. So I have 1 degree of freedom for this problem. The only degree of freedom is on the z-axis. I have already said that. So I'm writing down the equation of motion at the z-axis. Sigma fz will be equal to m times z double dot, which will also be equal to minus mg. Here we have minus because the gravitational force is opposite to the direction of the z-axis of the inertial frame of the body. Okay, so if we cancel out these m's, z double dot will be equal to minus g. So what type of differential equation is this? We can write down the equation in this form also: d square z over dt square equal to minus g. So this equation basically is a second order. If I want to classify this equation, I can say that this equation is a second order, since we have a constant at the right hand side of the equation. This is non-homogeneous. We don't have a partial differentiation here, so this is an ordinary differential equation. So how to solve that? We already memorized the solution of the equation from the high school courses. So we will integrate this equation 2 times to calculate the velocity and the location or a position functions. So if we integrate this equation once, we will get z dot will be equal to, of course, dz over dt will be equal to minus gt plus an integration constant c1. This will be v of t, the velocity of the single body. If we integrate this one again, integrate this one, integrate, z will be equal to, z of t will be equal to minus 1 over 2 gt square plus c1 times t plus c2. This is my second integration constant, by the way. So how to, if I want to solve this equation, or if I want to determine the motion of the body, I need to find these c1 and c2. So I need to use the initial conditions for both velocity and the location in this and this equations. So I can continue on the solution. So at t equals to 0, which means at initial conditions, my problem says that z0 will be equal to, z at 0 will be equal to z0, like in here. So if I put t equals to 0 in those equations, z0 will be 0 plus c2 will be equal to z0. So I have already found the first or second integration constant using this. At t equals to 0, we will have v0 will be equal to 0 plus c1, which is already given in question as v0. So I have calculated both integration constant using this initial conditions. My whole solution will be like this. V of t will be equal to minus g times t plus v0, and z of t will be equal to minus 1 over 2 g times t square plus v0 times t plus z0. So you are basically probably familiar with these two equations from your high school courses. We can go to MATLAB and visualize our first analytical solution. I will start with the constant parameters of my problem. I have a mass of 100 kilograms. Gravitational acceleration 9.80665. I have a velocity initial condition of 0. Position initial condition of, let's say, 50 meters. Then I want to declare my state variables. V1 equal to 0, Z1 equal to 0, P1 equals to 0. I will use an infinite while loop, and I want to stop the loop with a condition. Why? Because I want to stop the solution where the parachutist here touches to the ground. So to do that, we can use if break structure inside while loop. Let me remember what was my velocity and what were my velocity and location functions. So vi will be equal to minus g times ti plus v0. zi will be equal to minus 0.5 times g times square of ti plus v0 times ti plus z0. So if my position reaches to 0 or it becomes smaller than 0, I need to stop my loop and break the loop basically. So if zi becomes smaller than 0, break the loop, then I want to increase my counter, of course. I will be I plus 1 and ti will be ti minus 1 plus, let's say, dt. So I forgot to declare my I variable and dt variable. So let's initialize I as 1 and dt as 0.001 for this problem. So I want to mention that this dt has nothing to do with the accuracy of my solution. It only determines the resolution of the graph we will see after running this little program. You know that we have already derived the entire solution by finding the functions of v of t and z of t. Okay. Now let's run our little solver. In the workspace I can see that I have no error here. I can see that my time, velocity and location, position, state variables are calculated and stored in double arrays. So I can plot my state variables using plot function. Let's say f1 as figure 1, subplot 2, 1, 1, plot velocity with respect to time, subplot 2, 1, 2, plot position with respect to time. I can insert labels for axis, say time, insert y label, position, I can insert a legend also here. Let's say analytical without aero. Insert x label as time. Insert y label as 50 meter per second. Insert label legend as analytical without aero. Okay, if we look at these graphs briefly, we can see that our position initial condition is true and starts from 50 meters above the ground level, and it approaches to minus 0.02. Basically this is ground. Here at 3.2 second. If we look at the velocity with respect to time, we see a linearly increasing in negative direction velocity. It starts from our initial condition, which was 0, and it ends at a speed of around minus 30 meter per second. For the second part of our tutorial, we can get back to our physical model and modify this with an aerodynamic force, basically aerodynamic drag force acting on the body, and its positive direction will be the positive z-axis. I will denote this force by Fd. So we will be modeling the aerodynamic force as a second degree equation like this. Fd will be equal to 1/2 rho CD A and V square. We also know that the aerodynamic force, aerodynamic drag force, will always act on the opposite direction of the velocity vector. The problem with this aerodynamic force just starts from the beginning, as you see here. Because we have the square of velocity in our force equation formula, the sign of this velocity value will not affect the resulting force's direction. If it is negative, the result will be positive. If it is positive direction, positive. If it is towards the positive z direction, it will again have a positive direction. But in reality, if the velocity is negative, which means our body is going downward direction, the Ft must be positive, like this. If the velocity of positive, which means we have an upward movement, our body is going upwards, the drag force must have a negative direction with respect to this sketch. So to formulate this phenomena numerically, we can use the signum function, which returns the sign of its argument, in our case the velocity variable. So I will add a negative sign to my formula and add this signum function at the end of this formula. So let's check this again. If I have a downward velocity, this signum function will yield a negative sign, if v is smaller than 0, sign v will be equal to -1. So I already have a minus here, so the total sign of the formula will be positive, which means the same direction with the force sketched in here. And this is true. If I'm going downward, aerodynamic drag force must resist on me towards the positive z direction. This is true. So let's check the other way. If v is greater than 0, signum v will be +1, and I have a negative here, so the total sign will be in negative z direction, which means if I am going to upward direction, the resistance force will be to downward direction. This is also true. So this expression, this FD expression, can easily be implemented in numerical calculations, but in an analytical solution, if the velocity changes direction somehow, that means the governing differential equation has been changed. In this case, you will need a newer analytical solution with the newer initial conditions after the time at which the velocity changes direction. So you can solve your question by parts if your velocity is changing its direction. In our particular problem, I will try to solve the equation for a free fall or a downward or a motion with a downward initial velocity, so that I will guarantee the velocity to be always towards the negative z direction. So let us write down the equation of motion first. Sigma fz will be equal to m times z double dot, which also be equal to minus mg plus fd, according to my sketch here. In here, fd, so I already declared that my velocity will be smaller than 0, so the signum function will have a value of -1, so that the fd value will be 1/2 rho. This is the air density, by the way. This is the coefficient of drag. This is the projectional area of the body. So my FD will be like this: 1/2 rho CdA V square. So my equation will become like this: m times z double dot minus 1/2 rho CdA V square will be equal to minus mg. So I will divide everything by m. And I will put z dot, instead of z dot, I will write dz over dt, or basically v, velocity, into equation. And finally my equation will become like this: z double dot minus rho times cd times a over 2m times square of z dot will be equal to minus g. So if we classify this differential equation. This is a second order differential equation. It is non-homogeneous. It is ordinary again, and it is non-linear. I like to mention that I forgot to say that our previous differential equation without aerodynamic effects was a linear differential equation, so that we can easily solve that equation by hand. But we have here a nonlinear equation. Why? Because we have square of our dependent variable. We have square of z dot or v. The concern here, my concern here, is that the nonlinear differential equations can sometimes be cumbersome, if not impossible, to solve analytically or by hand. I'm not going to solve this equation, but I'm going to use Wolfram alpha for this purpose. So let me arrange my windows accordingly. I have Wolfram alpha here. I have my differential equation here. But now it is better to simplify the equation before entering it to the console of Wolfram alpha. Because sometimes Wolfram alpha gets confused about the variables and constants. So I can simplify the equation like this. This term will be denoted by k. So my equation becomes again z double dot minus k times square of z dot will be equal to minus g. Let me write this down here. Z double dot of t minus k times z dots square of z dot is equal to minus g. So let's look at our solution. Wolfram alpha also classifies the differential equation. You can control your judge here. So what is my solution for z, for position? It says that z of t is equal to c2 minus logarithm of cosine hyperbolic of square root g times k times c1 plus t over k. So so the solution comes up with two integration constants, c1 and c2, as it is expected since we have a second order differential equation. To solve for velocity for z dot or v, I will differentiate this z of t, of course not by hand again. I will use Wolfram again for this purpose. So dz over dt, which is v. Okay, let me write down the equation here. I will only write down this part of the equation, since the derivative of C2 is 0 and 1 over k is a constant. So logarithm of cosine hyperbolic of square root of g times k times C1 plus t. So Wolfram says that this is the derivative of the particular part. So derivative of C2 will be 0. I will have a minus here because of this, minus 1 over k times square root g times k times tangent hyperbolic C1 plus t times square root of g times k. So I can further simplify the equation to this level, minus square root of g over k times tangent hyperbolic C1 plus t times square root of g times k. Okay, this was v. To find my C1 and Ct, which are the integration constants, I will use my initial conditions again. So what we know is at the initial conditions at t equal to 0, v at 0 must be equal to v0, which will be equal to, if I put 0 instead of t here, that will be equal to minus square root g over k times tangent hyperbolic C1 times square root of gk. So we can write this equation like this again, minus v0 times square root of g over k will be equal to tangent hyperbolic C1 times square root g times k. If I take arctangent hyperbolic of the two sides, then arctangent hyperbolic minus v0 times square root g over k will be equal to C1 times g times k. So my C1 will be equal to 1 over g times k times arctangent hyperbolic minus v0 times square root of k over g. I probably have made a mistake here. It should be k over g, not g over k. Let me correct that. Here g over k, and here must be k over g. This must be also corrected. Now I can use my second initial condition here, which was at t equal to 0, z at 0 must be equal to z0. And that must be equal to c2 minus logarithm of cosine hyperbolic c1 times square root of g times k over k. So I can write this down like this. C2 will be equal to z0 plus logarithm of cosine hyperbolic c1 times square root of gk over k. This is my second integration constant. I already calculated the value of c1 here, you see. So you can calculate c2 with respect to c1 programmatically, easily. Now we can write down these equations to our MATLAB script and visualize our model with aerodynamic effects and compare the results with the first part, which had no aerodynamic effects. Again, let me start with constant parameters first. Constant parameters. I have the same mass. I have a projectional area which is 80 meters squares. It is quite reasonable for a parachute. So I have again gravitational acceleration. I have air density, which is constant. I have drag coefficient for the parachutist, 1.5. This is also a reasonable value. It depends on the geometry of both the parachutist and his or her parachute, but 1.5 is quite an average value. So my initial conditions are the same. V0 will be equal to 0, Z0 will be equal to 50 meters. I want to initialize my state variable arrays. Z1 I will declare my counter I equal to 1, dt equal to 0.001, start t1 as 0, and I will also declare this k variable before the calculation. K will be equal to 0.5 times rho times CD times A over M. That was our simplification while we were entering the differential equation into Wolfram Alpha console. I will use the same simplification in my MATLAB script. So I will also declare my integration constants before my loop because they are constant. C1 was what? 1 over square root g times k times arctangent hyperbolic minus v0 times square root of k over g. Okay, my C2 is equal to z0 plus logarithm of cosine hyperbolic C1 times square root of g times k over k. Okay, then start my infinite while loop. My v function was, velocity function was here, minus square root of g over k times tangent hyperbolic C1 times square root of g times k C1 plus t of I, no t. That was my integration constant. My function of v was like this. Okay, minus square root of g over k, tangent hyperbolic, c1 plus t. Okay, c1 plus t of I, ti, times square root of g times k. I hope I won't make a parenthesis mistake here. It will be very cumbersome to solve because okay. Square root of g k tangent hyperbolic. This is square root of g times k. This is tangent hyperbolic. Okay. So my position function was this. Z of I will be equal to C2 minus logarithm of cosine hyperbolic of square root of g times k times C1 plus Ti. This is the parenthesis of C1 plus Ti. This is the parenthesis of cosine hyperbolic. This is logs over k. I hope this is true. Now I also want to visualize the value of aerodynamic drag force, which was Fd with respect to time. So I will also calculate this separately here. Fdi will be equal to k over m times square of the velocity. Okay, Now we can write down the breaking condition for the infinite while loop. If zi becomes smaller than 0, break the loop, increase my counter after every marching step, increase my time with respect to my delta t at every step, plus dt. So I can end my while loop. Now let's run our problem. Okay. Now I want to clear my workspace and I will run my two scripts in order again. So clear CLC. This was my first solver for the first part. Let's run this first. Okay, these two was my first solution. Now I will run the second script with the aerodynamic effects. Okay, hold on. Subplot 2 1 1 plot t. Okay. Subplot 2 1 2 plot z with respect to t. Okay. Now let's make our labeling. Insert x label, time, seconds, y label, position, meters, upper part, insert x label, I want to insert my legend. The first solution was the analytical solution without aerodynamic effects, so I will denote it by this analytical without aero. Let's say analytical with aero. So grid on. Subplot 2 1 2 Insert legend. The first one was analytical. Without aero. The second was analytical with aero. Let's make grid on. So if we look at this velocity graph here, the solution of the model with aerodynamic effects has a velocity profile that reaches to a certain level, a steady state value, and this value is nothing different than the so-called limiting speed that you had already learned at high school. Basically, the limiting speed is defined for a falling object such that the aerodynamic force and the gravitational force on it, acting on it, are balanced out. So for our particular problem, what would be the value of this limiting speed, or can we calculate that speed analytically? So let's try this. Let's try to calculate this. The aerodynamic force was 1/2 rho times CD times A times, at limiting speed we limit square. The condition said that the aerodynamic force will be equal to gravitational force at this limiting speed, so I will equate this one to gravitational force. So if we we limit here, this will be like that. Where limit square will be equal to 2 times mg over rho times CD times A, then where limit will be square root of this expression, 2mg over rho times CD times A. So we have MATLAB under our hands. Let us calculate this value and see if it is comparable with the graph we have already seen. So let's calculate when vlim will be equal to square root of 2 times m times g over rho times CD times projectional area. Okay, it says that our limiting speed is 3.6527 meter per second. So if we let's go to the graph again. If we look at tools and data tips, so what we see here is 3.6527. It is the same value up to 4 digits. I believe that if we write down the limit for long format with long format, it will show us the exact value of this one. Now we have come to the main subject of this lecture, which was the implementation of Euler forward formula to solve a very simple differential equation. First we need to define what a Euler forward formula is, and what does forward or backward means in this context. So Euler formula of our concern here is basically an approximation to take analytical derivative of a function that comes from the famous Taylor series expansion. Basically, it is the truncated version of the famous series expansion. So let me show this on a graph here. So I have a function here, an arbitrary shaped function. Let's call this v of t. So I'm trying to calculate the derivative of this function at time t, let's say. So this approximation says that I can calculate derivative of this function at time t with 2 points, one of which is the value of this function at this point, the other is after this point, after a time lapse of delta t, let's say. Here I have t plus delta t. The value of this function at t equals to t is vt. The value of my second point will be t plus delta t. So I'm trying to find the derivative of function at this point, but I'm using these 2 points to approximate this derivative. So the original derivative will be like this. Let's say the angle between the x-axis of the x-axis of the graph and the tangent line is alpha. Normally dy over dt at t equals to t will be tangent alpha, right? But my approximation will say that dy over dt will be equal to v t plus delta t minus vt over t plus delta t minus t, right? So this is an approximation, by the way. Or I can write this like this also. This derivation will be limit as t goes to 0 delta v over delta t. Delta v will be equal to v plus t plus delta t minus vt. So in a programmatic way, I can also declare this equation like this. dv over dt will be equal to v I plus 1 minus vi over t I plus 1 minus ti. So this is basically delta t used in my numerical solver. Here I is the counter or element number of the current time, which is t equals to t. Okay. So what does this equation says to me? I am looking backward values to estimate the derivative of the function using the forward values. That's why this is called forward Euler formula. In other way, you can say that we can calculate the forward values of our function using the current values of our function. So this is like an estimation. We can accept that as an estimation. So in our formula, in our differential equation, we can use this expression like this. The external forces was equal to m times z double dot. These were external forces for our problem, which were gravitational and aerodynamic forces. At time t, current time. So if I put here d square z over dt, which is d over dt d of t in this equation, and use our previous expression for Euler forward formula. So I can write here like this: vi plus 1 minus vi over delta t. So I'm going to put this value here. M times vi plus 1 minus vi over delta t will be equal to sigma f, which were the external forces, of I, the external forces acting on the body at the current time, where my velocity was vi. So if we further simplify this equation, vi plus 1 will be equal to sigma fi, let's say, over m times delta t plus vi. So I'm sorry. So this equation means if I know the previous value of my state variable v, which is vi, or current value, let's say current value of my state variable v, and the forces acting on the body at the current time, which are whose sum are sigma fi. At the current time, I can calculate the next value of v in time, which is vi plus 1. So that starting from the initial condition, which was v0, at I equals to 0, let's say, v0 will be v0. We already give you that. We can find all the solution by marching in time with the steps of delta t. So I know v0, put it here. I know the forces acting on the body at time at 0, which means I at 0. I know my mass. I already know the delta t of my solver because I judged it. I put it on the solver that. So I can calculate vi plus 1, which corresponds to v delta t here. Or v1. So after that you will put I equals to 1. Now you know v1 from the previous calculation. v1 f1 over m times delta t will be equal to v2, and so on. So we are marching to a solution in time. That's why these types of problems or solvers are called marching problem. So in this context, what did we do until here? So we used Euler formula. And we have converted the differential equation to an algebraic one. So differential equations are hard to solve, but algebraic equations are easier than differential equations. We have converted our differential equation with Euler formula to an algebraic equation. You see that what was our differential equation? This was our differential equation, and we have converted to an algebraic equation. So let's write it again here. D square z over dt equals to sigma fz. This is a differential equation. Vi plus 1 equals to sigma fi, let's say, over m times delta t plus vi. This is an algebraic equation. So what if we write down Euler's formula in another form? Let's say d of vt over dt equals to, approximately equals to, vi minus 1 over Ti minus Ti minus 1. This is delta T, by the way. And use this in our equation. Again, m times dvt over dt, which is z double dot, vi minus vi minus 1 over delta t will be equal to sigma of f I. Now we can express this equation in two ways. I believe there is no harm in that. One, I can calculate my current state variable, which is Vi, using the current dynamics. That means current forces, Fi, and the previous value of my state variable, Vi minus 1. So I'm trying to calculate this using this and this. So another way, if I express this equation in another way, I can calculate my present state variable Vi this time using the present dynamics, sigma Fi, and the current value of my state variable. So I'm choosing my first expression here. So I do not know Vi right now, my current state variable. I do not know Vi, and I also do not know Fi, which is the current value of external forces acting on my body, because Fi is a function of Vi. We know that. So if we remember that, let's remember Ft was equal to 1 over 2 magnitude of Ft, let's say, rho times Cd times A times V square. So if I am calculating the value of Ft at I, this will be 1 over 2 rho times Cd times A times V square of I, right? I do not know Vi. I also do not know square of Vi, so that I do not know now drag force of my current time. So let's attempt to solve this equation. This was my differential equation, basically the algebraic version of my differential equation using the forward formula, equal to Fdi minus mg. This is constant, it doesn't change with respect to the counter or time. So I will divide everything by m. Vi minus Vi minus 1 over dt will be equal to, I will also put the explicit value of this force, rho times Cd times A times V square of I over 2m minus g. I will denote this constant part with k, just as before. So Vi minus Vi minus 1 will be equal to k times delta t times square of Vi minus g times delta t. If we regroup our nouns and unknowns like this, my equation will become k times delta t times square of vi minus vi plus parenthesis vi minus 1 minus g times delta t equals to 0. So what I see here is a polynomial equation in the form of a times x squared plus b times x plus c equals to 0. So here this term corresponds to my c constant, because I know vi minus 1. Right now I know this one. G is constant, delta t is determined by myself. B is minus 1, if you look at here. And A is k times delta t. My unknown is, it is obvious that my unknown x is vi. So if you solve this equation for vi, that means you will find the current value or future value of your state variable. So this equation might not always be a polynomial function like in our particular problem. So in general we have to use numerical root finding methods such as Newton-Raphson, which is an iterative method, by the way. So what can we say? We can say that if you are using Euler backward formula, you are both marching in time like explicit formula, like Euler forward, and every time step while you are marching, in every time step you are making iterations to calculate the current value of that state variable. So let's write this like this. Euler forward is a marching problem for our particle problem, by the way. Euler backward, we are both marching in time and at every time step we are making iterations in general. Because we need to have a root finding, we need to use a root finding method to solve this equation. Okay. Now we can make a simple comparison between Euler backward and forward formula. I will write this for you here. In forward Euler formula, is an explicit method. Because we are using the current dynamics, which means forces, with current state variable to calculate feature of the motion. Backward Euler formula is an implicit method because we are using or we are solving the current time current state variables and the dynamics, which means forces, which determines, for the forces determining those variables together with the previous value of our state variables. I hope I didn't make a mistake in this sentence. Backward Euler formula is an implicit method because we are solving the current state variables and the dynamics determining those variables together with the previous value for state variables. Okay. It seems okay. So for this lecture and for my particular problem, we will go on with the Euler forward formula. Now I will formulate my solution and then go to MATLAB to solve and visualize my solution. So my differential equation was like this: sigma f equals to m times z double dot, and Euler forward formula said to me that Euler forward formula said to me that v I plus 1 is equal to sigma f I over m times delta t plus vi. So I need to first calculate sum of the forces of my previous step, which is Fi, which consists of the aerodynamic forces of the previous step and the gravitational force of the previous step, which is always constant, m times g. So what was my Fd? It was minus 0.5 times rho times Cd times A times square of Vi times signum V. We have to remember this because of our sign convention. And of course we also have to calculate the position. So I will calculate the position using the velocity value, of course, with trapezoidal rule for this particular problem. So I need to give a brief introduction to the trapezoidal rule. So let's write here trapezoidal rule in a nutshell. Now let's say we have an arbitrary function with respect to time v of t, and I know that the area under the velocity curve will give me the position or the displacement of my body. So which is the integration of velocity with respect to time, basically. So let's say we will calculate the area between two consecutive points on my function. The first point is the value of my velocity at time ti. The second point is at ti plus 1, and the corresponding value of my velocity function at those points will be vi, and the second point will be vi plus 1. So I have this area under the curve here, and this is, you see that this is a curvy area. This edge of the area is a curve. But if the difference between those two consecutive points is sufficiently small, we can approximate this area, this curvy area, like a trapezoid, right? So how to calculate this trapezoid's area? I have, let's say, this area of this curve is SI. I can calculate SI with the short edge of my trapezoid, which is VI, plus the long edge of my trapezoid, which is VI plus 1, and average of 2 will be the average edge of my trapezoid, times the height of my trapezoid, which is Ti plus 1 minus Ti, nothing more than my time step delta T, will be my SI. Okay. To calculate the current position or the future position of the body, Zi plus 1, I need to sum Zi previous position value with my last value, Zi plus Si. So this is the sum of the trapezoids before Ti, and this is sum of the, or area of the last part. This SI is this SI. So we are on MATLAB again. I will use the same parameters with my analytical solvers to compare them. So I'm again starting with my equation parameters, constant parameters, mass, projection area, gravitational constant, air density, drag coefficient, my initial conditions, my state variables and their initial conditions. You need to start the indices in MATLAB from 1. So start the counter, my time step, also first value of my time series. Now I can start my infinite while loop again. So what was my equations? First I need to calculate the drag force. So F d I is 0.5 times rho times CD times A times square of VI times sine of V, sine, not V0, sine of V. Okay, so I can calculate some of my forces acting on that instance. So F I will be equal to drag forces at that instant and gravitational force m times g, and my VI plus 1 will be equal to, sorry, Fi over m. This Fi is sum of my all forces. Do not get confused with this sum operator here. Fi over m times dt plus the previous value of my state variable, velocity. Okay. Now I can implement a trapezoidal rule to calculate my position. Zi plus 1 will be equal to Zi plus, let's formulate this with like this, Si. Calculate Si first. Si will be equal to Vi plus 1 plus Vi over 2 average of them, times dt, and zi plus 1 will be zi plus si. Okay. I will also calculate my time series Ti plus dt. So please note that this calculation is not being used in my equations, is not being in my solution. I just need a time array to plot my graph, plot my state variables, velocity and position with respect to something, and this is that something. Then I have to have an if break, as I said earlier. If zi becomes smaller than 0, break my loop, and I will be I plus 1, and t I plus 1. Okay. I can end my loop, and let's see if we have a serious problem here. Okay, just warnings. Okay, I forgot to use the index of velocity array. Let's run again. Done. So from my previous part, I had this graph. This is the graph of the analytical solution with aerodynamic effects, by the way. You can remember from this limiting speed. So I will cross plot my numerical solution onto this one and see if there is a difference between them. So let me subplot 2, 1, 1 and plot t v with respect to t. Okay, I think it already plot that. So subplot 2, 1, 2 and plot the position with respect to time. Okay, let's see. I will change the color of the second curve to red, and I will increase its thickness if I can. Line width 2, 1, 1.5. Okay. For my position, use red, and thickness will be 1.5. Okay. So I'm a little bit surprised with the accuracy of my numerical solver. We see that they are exactly coincident. Solutions are exactly coincident. So we can get zoom in, see if there's a difference between them. Yeah. They're almost equal up to 5 digits. So let me increase delta t value and see if there is a difference. Okay, I will delete my numerical solution from here, calculate it with a coarse time step. Okay. Now tools, delete this one, delete this one. Let me change the time step, calculate it again, and plot again. Subplot 2, 1, 1. Plot z with respect to t. No, with respect to t. Okay, no difference. Good. I will delete that again. Clear. Subplot 2, 1, 1. Plot velocity. Okay, now we see the difference. Subplot 2, 1, 2. 2, 1, 2. Plot. Okay. Change this color to red. So you see that if I increase the delta t value, I'm getting away from the analytical solution. So if you remember the definition of Euler formula, the Euler formula was a truncated version of the Taylor series, right? We were truncating the terms in the Taylor series greater than 2. That causes the difference between the analytical and numerical solution. So if you increase this delta t value, you are basically increasing the effect of the truncated parts of the Taylor series. You can see that. So let's further increase this to 0.5, for example, and clear and run. And plot those variables again. Subplot 2, 1, 1. Plot t, e. You see that? this is the instability we have mentioned during the definition of the implicit and explicit methods, right? Okay. Now we are in part 4. You may have noticed that I can calculate or dictate every variable that is making up my solution inside my while loop here. I can change my air density in every time step, my coefficient of drag, my projectional area, my gravitational acceleration value, my mass value in every time step. I can change that. So this is very powerful. It is very powerful to use numerical methods or numerical solvers if changing the parameters of your differential equation is a necessity. So remember that the analytical solution with aerodynamic effects was already cumbersome to use, even with constant gravitational acceleration and air density values. So in reality, we know that both the air density and the gravitational acceleration decreases with the increasing altitude. So if I am going downward, what happens? G increases and rho also increases. This is the gravitational acceleration, this is the air density, and their directions are opposed to each other while I am going in downward direction. But if I'm going upward direction, I'm going on upward direction, so my gravitational force or gravitational acceleration decreases, and the air density, which means the aerodynamic force, also decreases. But here, if I'm going upward, my gravitational force will be on negative direction, and my aerodynamic resistance will also be on negative direction, which means their directions are the same. So I can understand from here, especially for high altitudes, during upward motion, using constant G and rho will falsify my solution, right? So I also expect that, unlike the solution with the constant parameters, we won't get a clean limiting speed, but maybe we can get a fluctuating speed because of the not perfect balance between these two, between these aerodynamic and gravitational forces. We had a velocity with respect to time graph of like this. And this value was, let's say, V limit, because there was a perfect balance between the gravitational force and the aerodynamic force. But because of the change in the value of gravitational acceleration and the air density values while moving, while changing our altitude, this balance will not be perfect at every time. So we may we may think that we won't have a constant V limit after some time, like in the solution with constant G and constant rho parameters. Okay. So to implement this story to our model, to modify our numerical solver, I will use two equations. One will be the air density formula with respect to the altitude, which will be like this. Rho of z, let's say, rho of z will be equal to some reference air density value at some reference altitude and temperature, let's say, e to the minus g0 times m star times z, current z, minus the reference z over r star times a reference temperature value. Okay, I couldn't find the reference for this. I just grabbed that from my previous scripts for my other problems. But if you want to use a more complex model, you have to consider the pressure, the humidity, the temperature values all together. My second formula will be the gravitational acceleration with respect to altitude, of course. G offset will be equal to G times G0 times, which is the reference gravitational acceleration at the Earth's surface, times radius of Earth over radius of Earth plus the location or altitude to the 2. So let me go to the MATLAB site again, and I have already written down these equations and added those equations in my solver in this script. Here, rho of I and G of I, just like the other parameters and variables. So let's run our model with the similar properties with my conditions, my initial conditions. I'll first run this. I will plot my graph. Let's say F1 is figure 1. Put it here. Subplot 2, 1, 1. Plot T and V. I will only plot the velocity values, not the positions, for this comparison. So let's hold on and run our second solver with changing gravitational acceleration and changing air density model. Same time step, run. So plot again T and V. Okay, let me insert my labels. Time and seconds, velocity in meter per second. Let's open up the grid. So if we look at the graph, for an initial location or initial position of 50 meters, we can't sense a big difference between the model with constant parameters and the model with changing parameters with respect to altitude. We can further zoom in to see some difference, but here, the difference is between the order of 1% meter per second. It is around this value. So let me increase the altitude and see what happens. Zoom out. So let me use subplot 2. 1, 2. Okay, I will run my solvers again with an altitude of initial altitude of 2500 meters. I will run the first. Now I will plot T and V. Okay. Hold on. Then I will run my second solver with 2500 initial position in meters. Run again. Plot again. So I want to focus on the initial part of my graph since the initial position is too high. It takes a lot of time for the body to reach ground, so we can't see these transient parts of the motion in detail. Insert Y label, velocity. Now we can see here that there is a big difference at the very beginning of our solution here. The model with the changing parameters, which is red one, with respect to altitude, has a bigger peak value here, you see. And after some time, since the gravitational forces initial dominance here slowly fades out, as you see, and it reaches to a balance with the aerodynamic drag around the 600 seconds here, you see. Now we're at the final part. I know that Adam's view is such an overkill for our simple problem, but I will use it anyway. Maybe that can give you an insight about using sensors, using measures, modeling aerodynamic forces to your more complex projects. So I also shall remind you that MSc1 software package is sponsored by Bias Mühendislik for the last 3 or 4 years to our university. I thank them on your behalf for this great facility. I also forgot to mention that our university has the academic license of MATLAB software, but I'm not sure if this license is sponsored or paid. So let's get started with Adam's view. with a new model. Let's say tutorial. I will use MKS unit system. Now the first thing I want to do is to scale my working grid. meters to 70 meters and 1 meter of spacing. Now I will add a construction frame for my earth fixed global reference frame here. I will add a point mass for my problem and rename its name as Paratrooper. Okay, what else we have? So the inertial frame of my body is at the position of y equals to 4. I will change it to 50 meters. Okay, and I also will modify my parts position with respect to the center of mass inertial marker. My reference frame will be CM. Okay. Now my body is at the same location with its inertial frame. I can clear or delete this marker too, but I don't have to do that. So let me control our model's degree of freedom first. From where I think it was here, model verify. It says to me that 6 degrees of freedom and there are no redundant constraint equations and model verified successfully. So this was expected because we know that in 3D space a single rigid body in 3D space have 3 translational and 3 rotational degrees of freedom, so in total 6 degrees of freedom if I do not have any joint. And it says that it basically uses the famous Grubler equation, which was number of bodies times 6 minus constraint joint constraints. So in my MATLAB models, I modeled the physical problem such that the body has a single degree of freedom, if you remember that. I don't have to do that, but since I know that my model doesn't have any lateral force or aerodynamic effect, it will have basically a single degree of freedom. So I will create a translational joint on y-axis direction between my part and ground. This will make no harm to my model. Basically, I believe it will decrease the computational cost of Adams solver. So using connectors here, I will create a translational joint, 2 bodies and 1 location. says that select the first body here. If you see, first body will be my paratrooper, second will be the ground. It says where is the location. I will add the joint between heart and ground on the center of my paratrooper. So its direction will be on positive phi or negative phi, doesn't matter, in this direction. So let's make this translation joint more visible. Modify now appearance and icon size, let's say 10. No, let's say 0.5. Okay. So what I need, I will create two measures, one for the position of my body with respect to the reference frame on the ground, and the second will be the velocity of my body. Normally Adam's wheel automatically calculates every inertial reference frame's kinematic properties, but I need to use those values in some equations. So I have to create those measures. So I will look at this design exploration, create a new measure. I will measure center of mass position of my paratrooper on y-axis. Apply. Okay, I will rename this measure accordingly. This will be position. Okay. I will create another measure as velocity and center of mass velocity of my paratrooper part, this part, on y direction. Apply. Okay. I want to see those scopes at my screen. So the second thing I need to do is I need to somehow make our solver know that the position of the ground. So the default ground in Adam's model is basically an earth fixed reference coordinate system, and it doesn't have a material or a contact property. So to keep things simple, Adam's view has a sensor tool. We will use this tool to automatically stop the simulation when our vertical position reaches to the ground. I mean, it becomes equal to 0 with a tolerance value. So let's create this sensor. The expression for our sensor will be a measure, the value of a measure. So I will create a runtime function here, and I have to get the value of an object whose type is a measure here. So I will select measures here, runtime measure, guesses, position. So I will click on insert object name, and my runtime function is created like this. So if value of this expression equals to this value with an error tolerance, which means in this case 1 millimeter tolerance, I will terminate my current simulation step and stop the simulation. Okay. So what else we have to do? Now I will create a single component force to replicate my aerodynamic force. So here in forces I will use create a force, single component applied force. Runtime direction will be body moving, will not be space fixed. It will move with the body, we know that. So it says to me that select the body, trooper, select the point of application. Let me select center of mass. So the positive axis, just like in our physical model, I will use the positive axis as upward. Now we need to modify the value for single component force with respect to our second degree equation. I will first rename its name by drag force. Okay, I will modify it, define use as a function here. So if we remember our equation, it was minus 0.5 times air density times coefficient of drag force times projection area times v square, right? But here instead of using a signum function like in MATLAB, I will just product the value first with the value of velocity and then the absolute value of the velocity. So I will add the sign of my velocity variable using this method. So I will use this measure as a variable in my equation. So runtime measure guesses velocity I will insert it here times absolute value of this. Okay. So this is also okay. I had used 0.001 seconds of time step in my own solver, so I will use the same value, but we should bear in mind that this is the output time step of Adams view. As far as I know, Adams uses an implicit solver or integrator, and this uses variable time step values. So we should remember this. Okay, let me first run the model without aerodynamic forces, so I will deactivate this. Let's restart this one. It's taking a long time because update graphics display is selected, so I will stop the simulation, untick this option, and if I run the simulation, it ends at time 3.19 seconds. So I'm looking at my position and velocity measures, and I think the direction of those measurements are true. So I can save my results like this. Let's name it as without aerodynamic, or without aero. Okay. Now I am activating my aerodynamic drag force and run the simulation again, and it ends at 13th seconds. Okay. I can visualize my solution with post processor here, and before that, let's save our results first. Let's say this with aero. Okay. Now in post processor I have two simulation results here. In first let me plot the position at curves. Position with my drag force, position of the model with drag force. This is also okay. In this new one I will plot my velocity values without aerodynamic force and with aerodynamic force. Okay, so I will export these values so that I can use them as arrays in my MATLAB script. Before exporting those values, I'm going to plot the variables for one model on one plot, so I won't get confused during importing those values in MATLAB side. So the first graph will be position and velocity of my first model. Export table. Let's say without aero. This is plot 4. No, this is plot 3. Apply, and I will make another plot 5, position, then velocity, and I will save this as with aero. Okay. Now I will add the results from Adams for the initial position of 50 meters and dt equals to 0.001 solution. I will use import data command of MATLAB. The results were in, I can see users. Here, without aero solution. I will use column vectors. This will be t atoms without aero. Position, atoms without aero, velocity, atoms without aero, exotrophs with unimportable cells, okay. I will also import the second model solutions. Go to the same folder. With aero. Okay. T atoms with aero. Copy this one. Position atoms with aero. Velocity atoms with aero. Okay. Now go to F1, subplot 2, 1, 1. Here plot T atoms without aero. Let me copy name from here. And velocity atoms without aero. Use this. Okay, it has been added here. Again, plot here T atoms with aero and velocity atoms with aero on the same plot, on the same graph. Okay. So let me change the legend names. Let's say ADM without aero and ADM with aero. Okay. Let me jump to the second plot. Subplot 2, 1, 2. Plot T atoms without aero and position. Okay. Plot with aero, with aero. Okay. Let me rename this as well. So if we zoom in further, we will see that basically we will see that the model without aerodynamic model, which was our handmade solution, is the red one, and the solution of atoms without aerodynamic forces is this green, and they are perfectly matching according to me for both velocity and for both position. here. So let me zoom out. Also here, I can also see that the model with aerodynamic forces in atoms also perfectly matches with our solver solution here. Let's go here again. See that the model with aerodynamic forces in atoms are very close to our analytical and numerical solution with constant G and air density. This is expected. If I have included the variable gravitational acceleration and the variable air density model in atoms somehow, it will be more like the solution like in the green. Okay. So I'm satisfied with the solutions and I'm satisfied with my solvers being very close to Adam's solution. Okay, I'm neither have a fluid mechanics profession nor I am a rocket engineer, but I feel we can say one or two things, or we can make brainstorming, a humble brainstorming here. So let us consider a rocket in a 3D space. This will be our z-axis, this will be y-axis, and we will have a z-axis here, sorry, x-axis here. Let's have an arbitrary shape like this. We may have some type of tail controls or stabilizers. We can have wing controls here, or we may have some type of control surfaces called the canard type surfaces at the front side of our rocket. These are wings, these are tails. So if this rocket body is a rigid body, this will be 6 degrees of freedom. Okay. Now let's think about the challenges for someone who tries to simulate the motion of this high-speed rocket inside 3D space. So we need to consider the 6 component of aerodynamic properties, right? 6 components: aero forces and moments. So you need to know the properties of drag, lift, and side forces. Pitch moment. Roll moment, yaw moment. So you will be going at very high speeds. The rocket may be sonic, transonic, supersonic, hypersonic, which is four times greater than the speed of sound, by the way. Here you have subsonic. You may interchange these two. So the aerodynamic properties will be function of Reynolds number or maybe Mach number, I don't know. I don't know this. So all the properties named here, drag, lift, side force, pitch moment, roll moment, yaw moment, will be functions of Reynolds and Mach numbers. So, and these properties will be changed with respect to your speed, so that with respect to Reynolds and Mach numbers. So a rocket may be going in subsonic sometimes, sonic, transonic, supersonic or hypersonic during its travel. So its movement is not limited to one speed level. So what else can we say? We will be going at very different altitudes. Which means you will have sea level, maybe beyond atmospheric level. So temperature is changing, pressure is changing, gravity is changing, air density is changing, so everything is being changed. So what else? Generally, to increase the maneuvering or maneuverability of the missile or a rocket, thrust force is used. What I mean by thrust force is you can change the direction of your thrust force like this. And this also have to be included in your differential equations, thrust vectoring. Let me write this down, thrust vectoring. So our little rocket will be burning fuel, which means mass value in our differential equations is being changed. So let me write this down. Moreover, the center of gravity is being changed. So we can't place the fuel symmetrically on a missile body. Because of that, the center of gravity is being changed while the fuel is being burnt. It depends on the missile, but sometimes more than half of a missile is being the fuel. So you may need to model the combustion process. Or make measurements using sensors about the combustion process. What else? So we will be going at very high speeds again, which means high aerodynamic frictions on the surface, on surfaces, which will change the boundary layer properties. Put a question mark here. Or this heat, because of the high aerodynamic frictions, may also affect the internal modules of the missile. That may be electronics, that may be warhead, that may be high tolerance parts inside the missile body. So or I have said that these are the control surfaces to control our guide for our missile. As you can understand, they are precisely controlled to guide the rocket along a trajectory or to target someone, something at the air or something at the ground. So they are being used to alter the aerodynamic forces and moments on the missile. So we are making use of these forces and moments to guide our missiles for a trajectory or a target. You see that that almost any term in those equations of motions for these 3 degrees of freedoms, none of the parameters in those equations will be constant. This is our problem. In our simple parachutist problem, we had a constant mass, we used constant gravitational acceleration, we have used constant air density, etc. But for a missile like this, for these degree of freedoms, almost none of the parameters are constant. So you have already probably heard the famous saying, "It is not the rocket science." So I hope this lecture will give you some insight about this saying. Rocket science is not a joke. I hope this will give you why we need to use numerical methods in mathematics to solve even the simplest engineering problems like paratrooper problem. And by numerical methods, let's say our final words. By numerical methods, we can add more complexity to our models to make them more realistic, such as adding aerodynamic effects into a free fall problem. And we can make those models solution basically possible. So that's all for this tutorial or lecture. Thank you for listening. Have a nice day.